Hey, everybody. Welcome back to another recorded Zoom meeting. Um, so like I said, it seems like most students won't be on campus anyway tomorrow, which is fine. Now, if any of this bothers you, this material either today or last time, you got to make sure you let me know. So shoot me an email, come see me on Monday in office hours, come see me on Tuesday in office hours, set up a time outside of office hours to meet. If any of this is confusing or whatever, please just let me know. So now we're going to finish off chapter 6. Please stop. Okay. So sharing my screen. So we're going to cover two sections because they're both short. The first is about what's called impulse functions, and the second is about a sort of a product rule for Laplace transforms. That's what a convolution integral does. Okay, so let's just jump right into it. I would try to make this as brief as possible. So here's the first definition. This is what a impulse function is. So the Dirac delta function delta is a function that satisfies both these properties. So it's almost always zero. So if you input any time value that's not zero, it's going to be zero as an output. However, the improper integral, if you look at the area under the curve across the entire t-axis, you get an area of 1. So if we were in class right now, what I would hope that I see on your faces is confusion. That doesn't really make any sense, what I just said. This function is like always 0, except at a single point. Like when t is not 0, it does something else, but otherwise it's 0. So that means it has no area under the curve. It's just camped out on the t-axis. And even though it has no area under the curve, the area under the curve is 1. That's contradictory and confusing. So the response really is, this is a function that physicists care about. And the physicist reaction is, well, don't worry about all that. So treat it like it's a thought experiment. So what you do is you put the word function in quotes. Just pretend like there's a thing that's like this. It's 0 almost all the time. However, it has some area under the curve. And why would such a thing be useful? Well, basically it models a spontaneous or instantaneous, I don't know what the better word is, an instantaneous large burst of force in the system. So imagine right at time 0 in this case. What if this were 0? Right at time 0, you flip a switch that shoots like, I don't know, 1,000 newtons into the system. You flip that switch on and flip it off at the exact same moment at time 0. So it's instantaneous. That's what this delta thing does. And if you do delta of t minus t naught, if t naught is 10, you're just saying that large burst of force happens at time 10. So the regular delta of t is sort of like centered at t equals 0. You can center this function wherever you feel like. And that's like, again, it's like saying at time t naught, in comes a big instantaneous force. So this function is definitely not continuous, whatever it is. So previous chapters can't handle it, but the Laplace transform doesn't care. As long as you know what the Laplace is of the delta Dirac function, you can slot these deltas into your problems, and the work goes exactly like previous ones, just like the previous section. So let me show you that. Again, we're not really messing around here. So I want to make sure my iPad is still going. Just gives you all the constants. Okay, except for the damping one. So it says damping is 5 when velocity is -5. So you should convince yourself that means there's a +1 there, because force is negative. Damping coefficient times -5. So the negatives cancel out. And that gamma is 5/5. Okay, now here's what's new. At time 5, a lot of 5s, okay. A large external force is, and here's the key word, instantaneously shot into the system. Now tell me what the mass does over time. So this sentence here means there's a delta of t minus 5 right there, a large instantaneous force at time 5. And the initial conditions are both 0. So how do you solve this problem? You Laplace transform it up, just like we've been doing. So you need to Laplace transform the right-hand side, and there's the theorem. So e to the negative 5s. Now, unlike what we've seen before, there's no over s here. If this were a u sub 5, there would be an over s right here. So these functions are actually kind of nicer than those step functions because you don't get a fraction. So 2y becomes twice ly, and then I'm sorry, this should be a y prime. Sorry, I just noticed that typo. So when you transform y prime, you get SL of y minus y of 0, which is 0. And then here, you get an s squared ly. And again, there's like a minus s times y of 0, then minus a y prime of 0, but these things are all 0. So you get this sort of nice little simple left-hand side. You divide everything over and you end up like this. Now, at this point, for you, you'll just ask Wolfram to invert the transform for you, because dealing with this denominator, as we discussed last time, involves completing the square. I've put the completing the square work here for you if you want to see it, but you are not expected to generate that on your own if you don't want to. So I'm just showing it to you here for completeness. And here I've broken it. I've said, well, you can like transform this because I want to emphasize the theorem that we ended class with the last time we had in-person class, just showing that, hey, if you invert this, you get some t stuff. And then what does the e to the negative 5s do? It causes you to pick up a u5 and shift t to the right by 5. So you take this function here, shove it to the right by 5, and pick up a u5. So I'm just showing you all that to emphasize previous work. But if this is you on an exam, you'll just ask, or in the homework, you'll just ask Wolfram to handle this for you, because I don't care if you complete the square or not. So I want to emphasize that certainly on an exam and hopefully in the homework, it's clear when you just use Wolfram and when you don't. So like, if this were an exam question, it would say somewhere here, you can use the Laplace inverse transform calculator. So it's clear that you can just do that at this step. So here I've done that here. If you want to be reminded of the syntax. So e to the negative 5s over that stuff, it reads it properly. And recall a theta of t minus 5 is actually a u sub 5. So this notation is extra confusing now because the delta function does use this t minus notation, but the step functions don't. So you just have to be aware of that. So this is u5, sine, the t has been shoved to the right by 5, e, the t has also been shoved to the right by 5. They switched the signs for some reason, that's fine, but this is a decaying exponential, and there you go. So there's the end result. And here, if you like, notice this function doesn't come online until time 5, because this u5 is 0 before 5. So this notation here, you don't have to write this if you don't want to. I'm just emphasizing nothing's going on for the first 5 seconds. And then starting at time 5, this function gets turned on. This is a sine wave with a decaying exponential attached to it. So it's a wave that dies down, and Wolfram will show you that. You see that graph? I don't know why it doesn't know the scale, but nothing happens for 5 seconds. And then at time 5, an instantaneous large burst of force enters the system. So it's an immediate hit up, right? That mass goes up, and I can't tell how high it goes because it cut the graph off. But then, since that force was instantaneous, it's like you've turned the force off at the same time. So there's nothing to keep the motion going after that, like away from equilibrium. So up, and then immediately damping kicks in and the motion will die down. So we've seen examples where like you turn on a force and then like it stays up here for a while. That's because that force kept going for a while. But this force doesn't keep going for a while. It gets turned off immediately. So there's no like wave up here where the damping and the force fight, because the force doesn't stick around to fight. Okay, so there you go. There's an example. So now I want to show you one that's fresh. If you hear screaming in the background, it's fine. My kids are always screaming. Okay. I don't know. I'm sure my daughter did something my son didn't like. That's normally what screaming means. Or my son, like, you know, barely scraped his finger and wants attention. It's also a possibility. Okay. So off we go. If you can't hear any screaming, then forget about what I just said. but I can hear the screaming. It's always convenient when the kids are screaming when I'm doing work. Like, I, sorry, honey, I can't help you with the kids right now. That's what I tell my wife. Anyway, okay, so here's a another example of fresh. What is happening? Okay, sorry, I just wanted to look at my other screen while I was doing this. Okay, so a 2 kilogram mass is attached to a spring with constant 2. This problem says nothing about damping, so I can assume it doesn't exist. Okay, so same kind of deal at time 5, large instantaneous force, and the initial conditions are both 0. So there you go. There's a initial value problem modeling this. And now this, as we'll see in a second, you can do this without Wolfram. This is sort of fair game because you can get things from the table without too much trouble. So let's go through the work. I Laplace both sides. And again, technically there's like this. If you want to write it, and I guess I did write it. And then on the other side, again, e to the minus 5s is the transform of that delta. There's no over s this time because it's not a step function. And then these just go away because of the initial conditions being 0. That's nice. So what you have is L of u equals, let me write it this way, e to the negative 5s times 1/2 times 1 over s squared plus 1. So you may want to pause here and see if you agree with that. But I'm dividing both sides by 2s squared plus 2. Right, 2s squared plus 2. That's what's attached to the L of u. And when I divide it over, I'm going to go ahead and separate it from that decaying exponential so I can use the theorem from last time. And pulling the 2 out of the denominator gives me something here that if you look at the table, that's pretty friendly. So let me bring up my table because I can never remember. Where are you? Okay. So yeah, this is a sine. That's just sine of t. Okay, so here's how we finish the problem. Whoa. U of t equals, so 1/2. I pick up a u5 from the e to the minus 5s, and then sine t minus 5. And there you go. Now you're done. So this problem here, if this were on an exam, I would say don't use the Laplace transform calculator. Like, don't do that. You don't need it. No completing the square. So here I want to see you work through the entire process. This is a perfect example of an exam type question because it's not too involved. There's only 4 lines of work. So it really is testing just, do you understand how the Laplace transform works? Can you transform both sides? Can you divide over? Can you do the slightest bit of algebra here, right, to write it like this? Can you write it like that? Do you know to write it like that with the decaying exponential siphoned off? And then you're done. So there's an example of an exam question. Okay. So now I'm going to switch off of my iPad. And I didn't realize my battery was so low, so I might not be switching back to it. We'll see, I guess. Okay, so come back here and I'll reshare this screen. Oh, and that previous solution, I should have mentioned that u5 sine of t minus 5. What does that mean? That means that the solution is a sine curve, but that sine curve only starts at time 5. And that makes complete sense because in that problem, there was nothing to start the motion initially. So all the action happens at time 5. So right at time 5, you smack the mass to get it moving, but it's an instantaneous burst. So the force is on and off. In this case, though, there's no damping. So there's nothing to kill the motion. So you smack it and then it's in a vacuum. So just up, down forever. There's nothing to kill the motion. So I should have pointed that out, but I panicked when I saw my battery was so low. Okay, so now let's go to section 6.6 about convolution. And this is a really nice conceptual section. And my impression is students like this as a little shortcut. Now, sometimes you can't do the shortcut because I'll tell you not to, but it's a nice idea here. And the basic idea is this. So like, if you start with this problem and you trace through it like we've been doing, you'll get this. Laplace of y is Laplace of y is, okay, sorry, I just want to make sure Zoom is working properly, is this thing. And so one thought you might have is, oh, I can take this product and break it into two pieces, this fraction. I can write it as 1 over s squared times 2 over s squared plus 4. And if you go to the table, this 2 over s squared plus 4 is sine of 2t in t language, and 1 over s squared is t. So can't you just be like, oh, that's a t, that's a sine 2t. So isn't the answer just this? Can't you do that? And the answer is no, you can't do that because Laplace transforms are integrals. And as you all know from, I mean, any calculus sequence class, integrals and products don't like each other very much. That's why integration by parts exists and is obnoxious. So unfortunately, you can't do that. So just generally speaking, if you have capital F of S times capital G of S, like S stuff times S stuff, can't you just write down the T versions of those from the table? Or more formally, when you invert, can you just individually invert pieces? And I left some space here. That space is for you to write the word no. So go ahead and write that down. Make it like as big as this entire area here. No, you can't just do that. But that raises a question. I mean, this is a product here. So isn't there some kind of way to deal with products? Like that would make no sense if there was nothing to say here. So this section basically just answers the question, can you do something with this without doing partial fractions or something, right? Like here, you could just do partial fractions here, but suppose you're like, wah, I don't like partial fractions. You know, I don't like having to break things into pieces like that. I just want to notice the product breaks apart real easy and then deal with that. The answer is there is a way of dealing with that, but it requires a definition. This definition will appear as if it's coming out of nowhere because it kind of is. So let's sidetrack for a second. Let's take a little excursion and let me give you this definition. So if f and g are functions, their convolution denoted like this, so like a fancy multiplication symbol. So what I'm going to define for you is a type of multiplication. It's very wacky from your perspective, but here it is. F convolution g is defined like this. The integral from 0 to t, and then you introduce a dummy variable tau. And you shift f to the right by tau, and then just replace all the t's inside of g with tau. Or you can do it the other way. So you pick like which function you want to just replace t's with tau's, and which function you want to shift to the right. Integrate from 0 to t. So notice tau is just a dummy variable. So this integral is with respect to tau, and you're integrating from 0 to t. So the end result here of this integral will be a function of t. So here's an example, the convolution of the function t and e to the t. I'm using this definition here. So t, I replace t with a t minus tau, and here's e to the tau, integrate from 0 to t. This right here, negative t plus e to the t minus 1, that is the convolution of t and e to the t. So when you multiply t and e to the t using this sort of funky notation here, that's what you get. And as with pretty much all integrals we'll deal with, I mean, this one you should be able to handle, but we'll just sort of punt off to the computer. So if you want to do this in Wolfram, I don't know how to type a tau. Maybe you people do. So you would do it like this: integrate t minus x. Just give it another name. From, so this is a tau integral, right? So I'm just using an x instead of tau, from x equals 0 to x equals t. So notice that, like, that's just a tau, 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 and there's the answer I got. So you can do that in the homework if you have to do a convolution. Just use this definition. So speaking of you in the homework, if I give you this function and this function, t squared plus t and sine of t, what's their convolution? So again, you can pick whichever of these definitions you like. It'll give you the same answer. So let's come here, integrate. I'm going to keep my from tau equals 0 to tau equals t. Okay, so let's give f the shove like we did a second ago. So there's f of t, but I've replaced all the t's with t minus x's. So not a t squared, but a t minus tau squared. And then I got to multiply that by g, where its t's are replaced by tau. So here's f, here's g. There you go. That's their convolution. So you can write that down. So again, you should just think of this as like a wacky multiplication, like t squared plus t times sine of t, that is what it is, right? But t squared plus t convolution sine t, that multiplication is this function. Okay, now a question you should have is, why do we do that? What's the deal with that? Where does this integral come from? Of what use is this? What does this have to do with anything? I thought we were doing like Laplace transform stuff. So check this out. This is going to blow your mind. The thing is, S land and T land are different places, you know? So like in S land, what, 1 over S squared plus 1, that means the same thing as that sine of T in T land. So it turns out that multiplication in S land has a translation to multiplication in T land. If you want to take multiplication in S land and ask like, what's the T version of that? What would it mean to take multiplication in S land and create multiplication in T land? And the answer is convolution. That's the translation of regular multiplication from S land when you get over to T land. Yeah, it's pretty neat. I mean, and unexpected, right? Because if I just asked you like, hey, again, the same idea, multiplication over in S land, what do you think that looks like in T land? You're not going to come up with this, I don't think, unless you've cracked open your textbook or something. Okay, so in practical terms, what does that mean? Here was the example I was dealing with. So instead of doing partial fractions, you could be like, oh, okay, I can just replace this with a t. I can just replace this with a sine 2t. But when I do that, I got to take this little multiplication symbol and replace it with a convolution symbol. And then, you know, you do the integral and you're done. So there's the answer. That's the same answer you would get if you did partial fractions. But this is like a little shortcut, you know. So that's pretty nice. Okay, so let me let's be brave with my iPad. I'm going to show you this last example on my iPad. Again, this is like total amateur hour here that I forgot to charge this, but man, I'm committed now, huh? In too deep now. There's no way to like make this video again. This is my one shot. Okay, one note. So this question here is a pretty classic exam question. So what you have to do is recognize that you can break this product into two pieces like this. Because once you do that, this from the table, that's a big old smile. This from the table is also a big old smile, because that is, what is that, cosine of 2t. That is cosine of 3t. So what that means is that y itself is the convolution of cosine of 2t and cosine of 3t. So in terms of an integral, that's like this. Integral from 0 to t cosine 2 t minus tau cosine of 3 tau tau. And you can ask Wolfram for what that is if you want to. My iPad's going to die, so I guess I won't. But it would be just like what I just showed you. So that is then done. So that's nice. It's a nice little shortcut. But again, conceptually, it's super nice. Like, I really can't stress to you enough how neato that is, that that multiplication over here in the S language somehow becomes this convolution multiplication in T language. I don't have a good language analog for you, right? But what that means is like something that's say super simple to say in Spanish somehow becomes super complicated to say in English is kind of what's happening here. Because this multiplication, that's not simple. I mean, integrals, that's serious. You're not messing around when you write down an integral. But multiplication, right, regular multiplication, my first grader knows how to multiply stuff, but he doesn't know how to integrate stuff. So anyway, that's what section 6.6 points out to you, that you can sort of do a product if you want to, but when you go backwards, again, this little dot becomes this little star. Okay, hopefully this was clear. As always, it deeply saddens me when I can't see your faces and I can't talk to you one-on-one to ask you what you're confused about. So on Monday, we're just going to practice with Laplace transform exam questions, so you see exactly what those are like. Also, by Monday, I'll post exam review materials. I have them ready, but I want to update them, I think, to more accurately reflect what you might see when you take your exam over this material. But anyway, so Monday is just set aside just to practice with Laplace transforms with stuff you might see on an exam. And then Wednesday, we'll review everything. Everything means undetermined coefficients, starting back at 3.5. So 3.5 through 3.8, chapter 4 stuff, and then the transform. So we'll talk about all that next week. Again, if something is confusing you, I really do beg you to send me an email or come see me.